Every year, thousands of combat vehicles are produced worldwide, capable of changing the course of history. In terms of weight, that's hundreds of thousands of tons of steel, aluminum, and composites, transformed into something that has to withstand fire, explosions, and impacts. Imagine armor thickness of over 5.5 inches, an engine with 1,500 horsepower, and a cannon that hits a target from 2.5 miles away. But the most important part isn't the numbers. Hidden inside every tank are technologies that aren't written about in open sources. Watch until the end, and you'll find out what's usually kept behind the closed gates of defense plants. Every painting begins with a sketch, and a tank with a design project. The design must take into account the integration of modern materials, armor, electronic systems, and weaponry. The key materials are high-strength steel, composite materials, aluminum, as well as special armor. First, the hull is planned and manufactured. It's made from high-strength armored steel, which can protect the entire crew from enemy fire. The steel must undergo heat treatment to increase its strength. In some places, the hull is reinforced with composite armor made of special multi-layered materials. Their composition is classified, but it can be ceramics, metal alloys, and plastics. The steel plates are cut using a laser to ensure high-dimensional accuracy. The armor thickness varies depending on the part of the hull. For example, in the front section, it can reach 14 centimeters. The panels are joined by machines, specialized welding robots, which immediately and thoroughly check the seams for strength, as they must withstand great loads and explosive impacts. Then, special modules, protective screens, and mountings for fuel tanks are attached, and it is treated with an anti-corrosion coating. Some tanks are even equipped with reactive armor. The tank's turret is the second most important part, because it handles the fire control functions and contains the main armament. It's made from materials similar to the hull, but with a more complex shape. For the turret, thick armored plates are used, which are bent and stamped by special giant machines to get the precise shape. In some places, the armor thickness can reach 12 centimeters, and with the composite layer, even more. The engine is manufactured separately. The Honeywell AGT 1500 operates on the principle of a gas turbine, almost like the engines of aircraft. It has a power of 1,500 horsepower and can run on various types of fuel. The main materials for the engine are titanium alloys, which are capable of withstanding high temperatures, up to 2,200 degrees Fahrenheit. Also, heat-resistant steel for shafts and combustion chambers, and composite materials for some elements. The rotor blades are cut from titanium plates using laser and water jet systems. The stator parts are also manufactured separately and coated with an anti-corrosion coating. The compressor, which forces air into the combustion chamber, is made of lightweight alloys to ensure high performance. The chamber is made of heat-resistant steel, capable of withstanding temperatures over 2,000 degrees Fahrenheit. Its inner walls are coated with a special ceramic layer to prevent overheating. Each element is checked for its ability to withstand extreme rotations of up to 50,000 revolutions per minute. After manufacturing and checking all the parts, the assembly process begins. The main engine body is assembled from several sections that are connected to the compressor, combustion chamber, and turbine. The shaft connects the turbine to the compressor and ensures the transfer of energy. A cooling system is added to the engine, which uses air and oil to reduce heat during operation. A unique filtration system is also installed, which cleans the air of dust and sand, which is especially important for operation in deserts or steppes. The engine is installed on a test stand, where it is checked for maximum power, temperature regime, and fuel consumption. Tests are conducted for long-term operation under high load. The engine is installed on the tank chassis for testing in real conditions. Its operation is tested on various types of fuel, including jet kerosene and diesel. At this stage, all previously manufactured parts are joined into a single structure. First of all, The engine is installed in the hull along with the transmission. After that, the components of the running gear are added, including tracks, shock absorbers, rollers, and suspension, which allow the tank to withstand high loads on rough terrain. I was shocked by how it all looked. It's just so massive and powerful. During the integration process, special attention is paid to the installation of the turret with all its systems. The turret is mounted on a special bearing ring that ensures its smooth rotation of 360 degrees. After this, a 120mm cannon, stabilization, and aiming systems are integrated into the turret. Thermal imagers, laser rangefinders, night vision devices, and other electronic equipment for the crew are also installed. The fire control systems are connected to a central computer that synchronizes data from all sensors. The ammunition is located in a special compartment with blast-proof panels, which ensures the crew's safety in the event of shell detonation. Next, auxiliary systems are installed, such as the air conditioning system, which ensures the crew's comfort in extreme conditions, as well as systems for protection against weapons of mass destruction. Elements of additional armor, including composite and modular blocks, are added to the hull. For each tank, protection options are individually selected depending on the assigned tasks. The next step is the installation of all electronic systems. All cables are placed in special channels for protection against mechanical damage. Each tank has to go through multiple levels of testing. First of all, the tank is checked for the tightness and strength of the hull. In special chambers, the hull is subjected to high pressure to ensure there are no leaks or cracks. To do this, the hull is filled with compressed air or liquid, and the outer surface is covered with a special solution to detect even the smallest defects. This stage is especially important, as the hull must withstand the pressure of a blast wave and provide protection for the crew. Special attention is paid to checking the running gear. The tank is driven over obstacles that simulate real combat conditions: hills, pits, marshy areas, and sandy roads. On test ranges, the tank overcomes slopes of up to 60 degrees, which allows for checking its stability and maneuverability. The tracks are checked for their ability to withstand constant impacts and friction over a long period of time. The suspension is tested for its ability to soften impacts during high-speed movement. The tank's weapon systems also undergo intensive testing. The 120mm smoothbore cannon is checked for accuracy and stability of firing on the move. For this, targets are set up at various distances on the test range, including targets located at a distance of up to 4,000 meters. In addition to the cannon, machine guns and grenade launchers are checked. An important stage is testing the fire control system, which must accurately synchronize data from the laser rangefinder, thermal imager, and onboard computer. The electronics of the system are tested separately. On special test stands, communication, navigation, and surveillance systems are checked. Special attention is paid to night vision systems to ensure a clear image in complete darkness or a smokescreen. The onboard computer is checked for information processing speed and its ability to operate in extreme conditions, such as high temperature, vibration, and humidity. The final stage is armor testing. On special ranges, the tank's hull is fired upon with various types of weapons: anti-tank missiles, shaped charge projectiles, and grenades. This allows for evaluating the effectiveness of the composite armor and additional protective screens. The armor must stop projectiles and minimize the effects of a blast wave. And only after completing all multi-level checks are the finished machines handed over to the military. What could be scarier than dust that glows with an invisible light? A rock that looks like ordinary gravel, but holds the fuel for power stations that light up megacities. So why is uranium called an energy marathon? Because to get just a few grains, you have to move hundreds of tons of earth, boil ore in acids, and turn it into a yellow powder that can kill with a single touch. And this is where the real alchemy begins. Toxic dust becomes a gas, and that gas becomes energy. But there's a detail they don't talk about publicly, and you'll only find it out at the end of this video. It all starts in the dust. And that's not a figure of speech. Uranium ore is mined in hot, arid regions. Arizona, Wyoming, Texas, New Mexico. Think cowboy country, but instead of lassos, they have drill rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is a scorcher, up to 100 degrees Fahrenheit in the shade if you can find any. There are two ways to get it. Open pit mining, where they strip the topsoil and haul the ore out with excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. Then there's the in situ leaching method. Pipes are driven into the ground, special solutions are pumped in to dissolve the uranium straight from the rock, and then it's all pumped back out. All this ore, a gray-brown rock, looks no different from ordinary stone. But inside it, uranium-235 makes up only 0.7%. The rest is mostly useless mass that doesn't work in a reactor. And to squeeze the required drop of energy from it, hundreds of tons have to be processed. That's why they say nuclear energy is quite the marathon. After mining, the ore is crushed, milled, and thrown into a chemical bath. Acid or alkaline solutions are added, which extract the uranium like coffee from a filter. Then comes filtering, precipitation, and drying at 500 degrees. And what comes out is yellow cake, a yellow powdered concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellow cake. It looks pretty, mustard-colored, fluffy, like a spicy powder for a Barbie. But God forbid you breathe it in or touch it. Alpha radiation, a long half-life, dangerous dust that gets into your lungs and settles there forever. It's handled only with respirators, suits, and behind 3 layers of glass shielding. Yellow cake is packed into double-walled drums, loaded onto escorted trailers, plastered with radiation signs, and off it goes to an enrichment plant. It's from this toxic dust that the journey begins, the one that leads to the white light of a lamp over your kitchen table, or the electricity in the subway hurtling beneath New York. Right then, the yellow cake has arrived, in drums, radioactive and dry as a desert wind. The next step, turn it into a gas. And not some lavender-scented air freshener, but uranium hexafluoride, the very same stuff from which the required isotope for reactors and other things is later separated. Let's cook, baby! The uranium concentrate is first dissolved in acid, purified, filtered from impurities, converted into uranium dioxide. And this is where the magic starts. The uranium dioxide is treated with fluorine in special reactors at a temperature of 1,000 degrees. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees. That means you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It's extremely toxic. It corrodes metals, destroys skin, and in moist air, it instantly turns into hydrogen fluoride and uranic acid, basically a deadly cocktail. That's why this is all done in sealed, automated reactors that look more like devices from an evil genius's lab. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, watching the gauges. Any mistake, boom or hiss, and you're in a hazmat suit, scrambling for the decontamination shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, drums with engravings, batch numbers, and a radioactive sign. Each one weighs up to 14 tons. And so, mission accomplished. The dust has been turned into a gas, ready for the most interesting part. Isotope enrichment. But don't get too excited yet. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think a washing machine spins fast? You haven't seen nuclear centrifuges that do 70,000 revs a minute. That's 10 times faster than a jet engine turbine. And all for one thing: to separate uranium isotopes. Uranium hexafluoride, that same toxic gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms are flung to the edge, while the lighter U-235 atoms stay closer to the center. A tiny microscopic difference, 1% in mass, and all this explosive technology spins just for that. But one centrifuge isn't enough, so they're connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so it goes, cycle after cycle, until the U-235 content reaches at least 3 or 5%. That's the reactor-grade standard. For weapons, of course, they follow entirely different routes, which are classified and under strict international control. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark gray color. This powder is pressed under 20 tons of pressure into small cylindrical pellets, 3/10 of an inch in diameter. They look almost cute. But each of these little pills holds an energy equivalent to 17,000 cubic feet of natural gas. Next, the pellets are sintered in furnaces at almost 3,000 degrees to make them as strong as porcelain. Then they're polished and ground. Perfect dimensions are crucial for a tight fit inside the cladding. The pellets are loaded into long metal tubes. Fuel rods, usually made of a zirconium alloy because it doesn't rust, doesn't react with water, and can withstand insane radiation. Each rod holds over 300 pellets. The rods are hermetically welded shut and bundled into modules, fuel assemblies. They look like a frame of several dozen tubes gathered into a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly comes testing for leaks, uniform filling, weld integrity, and behavior under temperature. There are no small details, because any one of them could cost not just money, but lives. The finished fuel is packed into armored containers that can withstand impacts, fires, and falls from a height. Transportation is under guard on a special route with an escort, GPS, and mandatory 2 seals, 3 codes, and a dosimeter on every side. Because even in its peaceful form, this is dangerous stuff that commands respect. After all is said and done, what's left is the depleted uranium hexafluoride. They call it tails. It's a mix of isotopes that still has a little U-235, but not much. These tails are stored in steel barrels, in special supervised yards. But in the future, they could be reprocessed in next-generation reactors, squeezing out every last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It's removed, carefully by a robotic system, and moved into pools of water. The depth is over 20 feet. The water cools it and shields the radiation because the fuel is still hot, both physically and radioactively. There it rests for several years. Then there are 2 paths, either long-term dry storage in double-walled concrete containers or reprocessing. That happens in other countries, as the US mostly stores rather than reprocesses. In dry storage, the assemblies stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This isn't the end, but a new stage of life, slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect.